Welcome to this module number 1, lecture 2, and in this lecture I will discuss about the comparison of HVDC and HVAC systems. In the first lecture already we saw the evolution of the power system, where we discussed how the DC was phased out, that was low voltage DC, and then we took over the AC power system, and again now we are talking about this DC is going to be taking place only in the transmission system. So, to see why the DC is going to be popular in the transmission system, now I have to compare this AC with the DC system. See the limitation of HVAC transmission system. Here the first limitation of AC system is that the reactive power loss. The reactive power, as you know, that due to the inductances formed and also the capacitances formed in the transmission lines, and also there are so many elements that is corresponding to the reactive power loss, will be one of the concern in the AC system. Second concern is the stability. As you know, already I discussed even though in last lecture, the stability is one of the concerns in your AC system. If your system is highly loaded, though that system is more prone to the stability of the system. Another is current carrying capability. Here we cannot have a long cables, we cannot have a long transmission lines due to the huge charging, and especially in the extra high voltage system. And due to this, we cannot load the line fully to their thermal limit. Even though we cannot have a longer distance cable, so that even though charging, due to the excessive charging, it is not possible to have a long distance cable, and so that we have to go for the DC cables in that cases. The skin effect and the Ferranti effect is also prominent in the AC. The Ferranti effect basically says if the system is lightly loaded or unloaded, then your receiving end voltage is higher than the sending end voltage, and already I discussed in the last lecture that to control the Ferranti effect, we normally use the reactors. We have the three types of reactors. One is your line reactors, bus reactors, and the tertiary reactors. Skin effect is basically if the two conductors are there and the AC current is flowing. So, due to the effect of current and flux and the first coil, it will be affecting another coil, and thereby it will change the reactance and the impedance of the line. One of the major concern of the HVAC system is the power flow control. It is not possible to control the power in the AC system without using any extra device. If you are using flexible AC transmission system, which we will discuss later on, that then we can control in the AC system as well. But in the actual AC system, it is not possible to control. It depends upon the current will flow depending upon the impedance seen by the current. With these 5 limitations, if you will see in the HVDC transmission system, all these 4 concerns are eliminated, and that becomes the advantage of the DC transmission system. Means there is no reactive power loss at all, because reactive L and C has no impact on that. Then there is no stability concern, because there is no P angle delta curve at all. So, the stability concern does not arise, and thereby we can load our transmission lines up to its thermal limit. However, in the AC systems, we cannot load up to the thermal limit, especially for the long EHV transmission lines, because your stability concern will be one of the major concern for secure and the reliable operation of the power system. Another other limitation was this your charging, and here there is no charging, so we can go for the longer, as long you can have the cables, DC cables, and also the DC transmission lines without any problem. Similarly, there is no problem of the skin as well the Ferranti effect. Again, these are arising due to the capacitance form or due to the flux linkage of one conductor with another conductor. So, that is also means it does not arise in the DC transmission system. Major problem of the DC system, AC system was the power control. Now, that can be eliminated, means we can control the power very efficiently in HVDC transmission system. As you know, this power control here, this in the DC system, we have the P, the DC is nothing but your VDC into your IDC. Now, this PDC can be controlled by either voltage or by controlling current or by controlling both. But normally what we do, in HVDC system, current is normally kept constant and the voltage varies. It is just reverse in AC system. In AC system, if you are writing the PAC, it is your VAC into your IAC and some multiplied by the power factor. In most of the AC circuits, if you will see, here, normally the voltage of that applied to the any appliances, it is fixed. We never vary this voltage. However, the current keep on changing, that is taken from the source. For example, if this is a source, this is your load, which is supplying your here, that's V AC you are supplying. If you are connecting another load, you have to connect in the parallel. What happens? The voltage across this is same, voltage across is the same, but the current drawn is now going to be changed due to this connection of the impedance. So the AC system always works in the parallel. This is different here. What we do here, we vary the voltage. However, the current in the whole link is a constant, only the voltage is changed. So the power control here, now you can say the power here that is taken from this source is basically the voltage constant, only I is changed due to the connection of the impedance. So this is the totally difference in the AC and the DC system. So this voltage here, normally we vary, and thereby we can control the power. More advantageously here, it is not that we can vary this from 0 to certain value, but it can vary in the both direction, means it can be negative also. So the flow of the power can be even though change in the one direction to another direction as well. If you will see in the, now there is two fundamental rules here in the AC system. Let us suppose this is your bus, this is your transmission line. Power, that is, let us suppose this is your voltage V1 angle delta 1, and this is your V2. Here I am taking as a reference, and this is X of the line. So we can write the power flow here P V1 V2 over X sin delta. Now if this delta is positive, means power will always flow from this direction, means real power I am talking, it will be flowing from this node to this node. Because this, if delta is positive, if delta is negative, the direction will be the change. And always the P in any transmission line is unidirectional, means here if the power is flowing, this power will be coming out, that will be flowing that direction. The magnitude may be different, and that magnitude difference is due to the losses in this transmission line. But it will be here flowing, it will be going out from this transmission line. If you are going for the reactive power, your Q, in the AC, here I am talking about the AC transmission system. The reactive power system here normally always flow. So here I can generalize this real power P flows from higher delta to low delta. So this is a general rule. By looking at the bus voltages here, angles, you can see whatever the magnitude here, if only you have to see the delta. And that is only true in actual operating condition. There is something other, sometimes voltage is so absurd, in that case it may not violate. So in actual operation condition, here the real power always flows from higher angle to lower angle. Similarly, the reactive power here, it flows from higher voltage to low voltage. That is also true. Now in this case, let us suppose this V1 is your 1.1 and this voltage is here 1. Now it shows that reactive power will flow from here to here. But it is not true, because that depends upon this transmission line loading as well. Because no doubt this voltage is higher compared to this voltage, but we don't know the voltage profile of this line, because there are some distributed capacitance in the line. That means the voltage may be up and voltage may be down for this transmission line. So if we draw the voltage profile of this transmission line for the different loading, here the possibilities are, here your voltage is 1.1, here voltage is 1. So this voltage here is starting here to here, there is a possibility that voltage is here flat. Voltage throughout this transmission line, there is a possibility that it will from here, it is going to 1 per unit. But again, if the loading is less here, there is a possibility the voltage here is going like this. If loading is higher, the reverse scenario is there, maybe like here. So now you can see this concern here, the rule that is Q, reactive power always flows from higher voltage to low voltage, is still valid. But we have to see the voltage profile throughout the line as well, not only looking at the node. So that's why the reactive power can flow in either direction. For example, if you see this is the case, then your reactive power here will flow like here Q, and this will be going here Q, because always this end is higher than this end. For example, if you see this case, now this voltage is higher, somewhere in between the line, so the reactive power will be flowing from here to here, and this will be flowing like here, this is Q, and this side it will be flowing here Q. Now you can see the reactive power flowing in the both side, which is going to both nodes. And again, it depends upon the loading. This is the case when it is lightly loaded. And this voltage profile is coming due to the distributed parameter here charging of the transmission line. If the transmission line is long and lightly loaded, we can end up with this scenario. Similarly, if the line is highly loaded means more current flowing in the line. So this scenario may arise, and you can see the reactive power is flowing here, and here also reactive power is flowing. So the Q here, we cannot say it is unidirectional. However, the P is a unidirectional. It can flow in either directions. All the four possibilities are there. So in this is a general rule, and that is true for all transmission systems. And if voltages here are within the operating range. If it is a very absurd, let's suppose here 0.7, here 0.4, this scenario may not be valid. If you just write the equations, and then you can see the flow of the power. Now let us see some more other advantages other than the major advantage which I discussed. Those advantages, 5 advantages, were basically just opposite to the disadvantages of the HVDC system. So that I said there is no reactive power loss, no stability concern, no charging current, no skin and Ferrand effect, and the power control is possible. Some other minor advantages are it requires less space compared to the AC for the same voltage rating and the size. Now you know why I am talking, because in the AC always we design our system, and AC it is this, we always design for its maximum peak value. However, we calculation here, we always take the RMS value. So here I am saying for the same rating, if you are talking about the RMS, same RMS here and here the DC value, you have to design your system for this peak value, means you have to multiply it by √2. So you require more space for your clearance, you require more towers spacing, etc., and that's why it is said it requires less space compared to the AC system for same voltage rating and size, because we have to go for the peak value here under √2 times. Another concern here is, means advantage here is ground can be used as a return. In AC system we cannot use ground as a return, because due to the frequency, you know, the penetration comes into the picture. But in the DC, the ground can be used as a return, and thereby we can reduce, at least suppose you are working as a DC here, the positive polarity, then you can use your ground as a return current. So you require only one conductor that can even though give the power to your load end. However, in AC, at least you require 2. One is your positive, another will be return conductor or neutral conductor. We will see, although this is advantage, but normally it is used rarely. It is used only in the emergency condition. Because even though you are using ground here, there may be so many pipes, so many things are underground, that will be the erosion and corrosions in that system. So it is used only during the emergency condition. Suppose there is some fault in the system, then we can use ground as a return. And also to make it this, we'll see the grounding rods, etc. Those are used in the substation. We'll just discuss when we'll discuss about the components of HVDC system. Another advantage that it requires, means HVDC transmission system gives less corona loss and the radio interference. Corona loss, you know, the empirical formulas are there. It is always your corona loss P is proportional to F into 25. F is operating frequency. In the DC, F is 0. So always it will be lesser compared to the air AC. And also that is another factor, even though weather is bad, then this loss also very excessive in the AC system. However, it is very less in the DC system. The radio interference also related with the frequency. If the DC system is there, it doesn't affect this other communication system, but it is affected by the communication wire. But if it is AC system, this frequency 50 hertz or 60 hertz, that will affect your communication system as well. And that is why there is radio interference problem in HVAC transmission. Another advantage here, it is cheaper for the long distance transmission. To understand this, here let us see the break-even points for AC and DC. Normally, if you see the cost characteristic, this is your distance and this is your cost. Then if you will see your this AC system, here it is going like this, and your DC system, sorry, this is a not so straight line, it is somewhere here like it is a DC system. So now you can see here, initially the DC system is more expensive, means if the distance is less, and this point is called your break-even point. This break-even point means if your distance, you are going to transmit power for longer distance, here more than this distance you will find the DC is cheaper compared to the AC. So initially you will find the DC is more expensive due to the terminal equipments. We require the converters, we require the substation and so many other auxiliaries, filter, smoothing reactors at the substation, and those are very, very expensive. So that's why the cost of the DC in the initially here it is very high. But if you are going for the long distance, including those here, if you will see this AC becomes more expensive. Now the question arises, why if the distance increases, then AC becomes expensive? This is only due to if this AC distance is increasing, you have to go for the compensation due to the huge charging. You have to use some intermediate station compensating devices to control the voltage in the transmission system, and thereby you have to have a substation, and this will be more expensive. Earlier this distance was more than 800 kilometers, the break-even distance, but now due to the advancement in the power electronics devices, and now they are commercially cheaper available, so this distance has come down to 600 kilometers even. So if you are going for more than 600 kilometers, this DC becomes better option compared to the AC option. But nowadays this is not only true, because this HVDC system is not only used to control to flow the power from one distance to another distance. One advantage of the DC, as I said, the power flow control. Sometimes we require to power control from one area to another area. Distance is not larger, but boundary is there, so it is the distance maybe 10 meters, maybe 1 kilometers. For that purpose also, now we are using the DC system, and that is called back-to-back connections. Means converter and inverters are with the same substation maybe. So that intention is to control the power only. Then the distance is not significant for us, because this is the only we are calculating the power, bulk power transmission system. If our intention is to control the power where it is not possible here in the AC system, if we only want to control, then we should not see the cost. We have to go for this DC system as well. But if you are going for the bulk power transmission and the distance is more, you have to go for your AC system. Even though you see in India, we don't have any transmission line more than 500 kilometers. That's AC transmission system. But the DC transmission system, we have more than even the 900 kilometers. Even from Rihand to Dadri, there is a huge, it's a big transmission line. It is approximately, I think, 800 kilometers. It is 1500 megawatt is flowing from the Rihand to Dadri. And we require that power because our Delhi and NCR region, we require huge power, and going over that. I'll come to those points later on. So here, I want to tell you the cost. If the distance is more, this is going to be cheaper, otherwise this is going to be expensive for the bulk power transmission. So that's why it is written the cheaper for the long distance. Long distance means more than the break-even, otherwise it will be expensive. Another advantage here is the asynchronous operation is possible. You know, in the AC system, always the frequency of the interconnected system should be same in the steady state. But in the, suppose you have the two frequency system, you cannot connect by the AC system, and the option is that you have to connect by the DC system. For example, if you are having here one system, this operating at certain frequency f, and another system here you are having frequency 2, then you cannot connect here by AC, it is not possible. So, what we can do here, we can use by the DC interconnections, we can have the DC here and then it is possible. So, this is called asynchronous connection, means two different frequencies can be connected with the help of the DC lines, and that is one of the another concern. Suppose you have a one island of the operating the different frequency, mainland is operating different frequency, then the only option that you have to go for the DC system. Another advantage is basically the no switching transient. You know, the switching transient basically arises due to the energy storage elements, that is your L and C. If your circuit is purely resistive, there will be no transient at all. But the presence of these two elements, and which is very common in the AC system, and the transient arises. And again, the transient magnitude depends upon their magnitudes, their distribution or the number of elements, it depends upon that. So, in the DC system, there is no, because this L and C in steady state there is no L and C. Although we use the smoothing reactors are there, but only you are switching, then it will be there, or after that there is nothing. And here this is more prominent in AC system. Another advantage here is no transmission of short circuit power. What is the short circuit power? In the AC system, normally if you are keep on connecting the several lines at one bus. Let us suppose this is a bus where so many lines are going. Then if what we do, we calculate the fault level at this bus. We go for the three-phase short circuit and we calculate what will be the fault level if there is a fault here. And this is basically, this fault is contributed by these lines. So, if you are going to connect another extra line here, what happens? The fault level of this bus will increase, because the impedance seen by this point to the ground will be again the parallel line you are connecting, the impedance will keep on increasing, means fault level will increase. That is short circuit current, I can tell you. What happens this? There are so many locations here, even though in our UP itself, so many buses are there, so many lines are connected, and thereby huge short circuit current is there. So, if there is any fault, bus fault here, the circuit breakers here, they must be tripped. And the rating of these circuit breakers are basically decided by this fault level. There is case if you are connecting so many lines and some fault occurs, the rating of the fault current will be much higher than the circuit breaker ratings here. Even though sometimes what happen, you have the, let us suppose 3 lines, you are connecting 4th lines, that is going to change the fault current level, you have to change even though sometimes the circuit breakers of this line. Because these circuit breakers are decided, they are having some standard rating, maybe it is 40 kiloampere, 63 kiloampere. If the fault level is more than that, then there is no option. You have to go for another option. What we do, we go for the bus splitting. Bus splitting means what we do, few lines are connected here, then we have another line and the few lines are connected here. So, that reduce the fault level, and thereby we can save the cost of the circuit breaker replacement. So, even though our UP system, the several locations it is planned, when we are going to expand our network, this bus splitting means same position we have the 2 buses, so that fault level can be reduced. So, but now how it is advantageous if you are having the DC system. Let us suppose I want to connect here DC system instead of AC system. What happens if the fault occurs? This will not contribute any fault, because this control is very fast. So, no current will contributed by this. So, this is just blocking the fault current from this line, and this is one of the advantages of this HVDC system as well. So, that is why it is here it is written no transmission of the short circuit power from another side on that bus. So, it is advantageous in that case also. Another advantage is that the no compensation problem. The compensation, I mean to say that if you are having a long transmission line, then this transmission line will have your, this is a distributed parameters, this is your RL, and we can say the capacitance, and it is the distributed throughout the line. What happens due to this capacitances? We have to compensate it, otherwise what will happen, the sum of the mid of the voltage will be very high compared to your sending and the receiving end, and there will be the flashover. So, what we do, if line is very long, we have to use some compensating device in the intermediate, so that we can absorb some of the reactive power generated by these capacitors, distributed capacitor. However, in the DC, this concept is not there, and thereby no compensation is required. We can operate line very smoothly. Another advantage is this low short circuit current. This is related to this. It is blocking also here, as I explained. It is blocking the short circuit current flowing from this line, and also even though you are connecting, it is not contributing in this fault current. So, the fault current level here is also going to be reduced by this HVDC system. So, this basically reduces your fault level of that bus. Another advantage is that the fast fault clearing time. Due to the switching, these are the very fast switching devices. We can control them very effectively, very efficiently, so that we can maintain the stability of the system by controlling these switches appropriately. And that is why the fast clearing can be done. If the fault is occurring in this line, let us suppose this is a DC line here. Here, if fault is occurring here, we can control these two switches, so that this fault cannot be propagated in the AC system, and very fast we can control this, the fault can be cleared. Because in the AC system, the fault clearing mechanism, if you know, there are relays. They will sense whether there is a fault or not in the system, and this relay will give the command to the circuit breaker. Circuit breaker will take some, because it is a mechanical device, it will take some time, and then it will try to open. So, this mechanical system always it will be sluggish than the electronic system. That is why this is the HVDC system fault clearing is very, very fast compared to your, this is a conventional AC system. So, these are the basically the major advantages of HVDC system. There are so many minor will be also there, but I am not concerned about this. So, I discuss some of the major, and then some of the, you can say, not so major, but it is still very significant for the HVDC transmission system. So, we saw this advantage of HVDC system compared to the AC system, but we should not forget no system is free from some problems, and therefore, this HVDC transmission is also having some problems, and those problems are listed here. You can see I have written the cost of the terminal equipments is high. It introduces harmonics. It blocks the reactive power, although reactive power sometimes we require from one area to another area, it is blocked. Another concern is the point-to-point transmission. I will explain all this, and then it has a limited overload capability due to the power electronics devices. They are having the limited overload capability, and although DC system does not require any reactive power, but still you will see at the converter station we require huge reactive power supports, basically the smooth operation of converters. I will explain one by one. First one is the cost of the terminal equipment is high. Already I said that here, even though if you are going for the long distance transmission, you can see even though distance is very small, some cost is required, and that cost will be associated due to their inverter and the converters. They are the very expensive device. It is not converter, even though we require some cooling device for the converter and inverters. We require some filters, because the filters are used for controlling some of the harmonics. Filters are there, they must be cooled. So many auxiliaries are required in the DC transmission system, and that is why the terminal equipments are very expensive. You know, now even the cost is not so expensive, because due to the advancement in the power electronic devices. So, the cost is going to reduce, no doubt, but still it is higher compared to the AC. So, if you are going for an AC substation of same rating, if you are going for the DC substation, you will find the cost of the DC substation is more compared to your AC transmission system. But we hope in future again the cost will be keep on reducing due to the advancement in the power electronics technology, and let us see in the future. Another concern is the introduction of harmonics. In the beginning, as I said, it was the valves. Now then we moved to the thyristors. Now we move to the GTUs, and now we are talking about the IGBTs for this the converter technology. When we were using the thyristors, they have some inherent problem that it was not able to turn off automatically. We required some turning off components or some devices to turn it off. But now with the help of GTOs we can turn off, and we can go for the pulse width modulated converters, thereby we can reduce the harmonics. So in the conventional gate thyristors, basically we were having the harmonics, that is n p plus minus 1. This is the harmonics component, where n is your integer, p is number of pulses, and here 1 is again the real value. So if you see for 6 pulse converter, if you are using the conventional thyristors, so you are going to have the 5th, 7th, then you are going to have 11th and 13th and so on. So these are the harmonics are present, and these harmonics are called the characteristic harmonics. Even though other than these harmonics are also present in the system, due to the overlappings of one valve is conducting, another is going to be off, it will take some time, and due to that we are going to have some uncharacteristic harmonics other than these in the system, and that if you are not, they are not filtered out properly, they are going to propagate in your AC system, and that may create so many other problems that we don't want. No doubt once you are going for higher order harmonics, the magnitude are keep on decreasing. The magnitude of this will be highest compared to your higher order, but still if you are having so many devices in any area, so your harmonics component which is going to be injected in the system will be more if you are not using the filters. But now even with the help of pulse width modulated converters, the harmonics levels are going to be reduced, but still it is not free from harmonics, because this is a switching device. So any AC signal that is switched on and off, it will certainly generate some harmonics. Maybe the magnitude is less, but still it is going into the system. So introduction of harmonic leads that we have to go for the filter option, but it is not possible to go or to filter out all the harmonics. We allow some of the harmonics to enter the system, and if the magnitude are less, but that is if you are having perfect sinusoidal, that is always better and it is desirable. Another is the blocking of the reactive power. As I said, this here, this you can imagine the two systems, let us suppose they are operating on the same frequency even, hardly matter, and it is connected by the DC link. The reactive power which is here cannot flow from this end to that end, because here in the DC there is no reactive power concept as well. Now the question arises again, why we require the reactive power here? Normally the reactive power concept is the local phenomena. We don't want the reactive power should flow from this remote end and this should go here. Reactive power normally should be compensated locally, because it is related with the voltage. However, the real power is a global phenomena, that is why the frequency of the whole system is same. Now, but sometimes during the emergency condition, let us suppose this system needs somewhere, there is some fault here, some problem in this here, temporarily we require some reactive power support from another region. And if it is an AC system, you cannot provide even though that reactive power support. So it blocks the reactive power from one end to another end, and sometimes we require this reactive power should flow from here to here or here to here, and that is a problem with the DC system. The fourth problem that is very important is called point-to-point transmission. Point-to-point transmission means that here if you are one converter is there, another inverter is there, means you can not tap the power in between. Means if you are supplying the power from one end, for example, if I will say here this is your sending end, this is your DC line, this is your inverter, here 3 phase, the tapping power in between is not allowed in the DC system, because here this power flow control or power flow is maintain the current which is flowing here, it is made constant. If you are tapping here, then must be this converter should know where the power is, the current is flowing. But in AC system, wherever you want, you can just tap the power, you can put the CATIA and you can take the power wherever you want. But in DC system, the point-to-point transmission means here if you are injecting power, you are going to draw the power at this point only, means in between you cannot take. So this is called the two-terminal HVDC link, means terminal 1, here terminal 2. However, nowadays even though multi-terminal HVDC links are also possible, So what we do here, there is a possibility we can have another link here and we can have another terminal here. So now it is a 3 terminal, means for tapping the power you must go for another terminal, and if you are going for more and more terminal, it becomes more and more complex controller. We will see the controller later on, that even though for these 2 controllers they are communicating the signal to each other. Now if you are having another terminal, now all these 3 will be communicating to each other, and if you are going more, then it becomes very, very complex. So this is called 3 terminal. So I mean to tell that the point-to-point transmission is not so practically feasible in HVDC transmission system. Normally it is from one end, power must be injected to another end, and that is a problem, that is a point-to-point transmission is not feasible in HVDC transmission. So multi-terminal HVDC link is also possible, and it is existing in the world, but only up to the 3 terminal, not more than that. And it is not desirable to go for multi-terminals here, because that cost will also increase, because if you are adding one terminal, it is not so simple. You have to go for all the substation here, the converters are there, and the communication and the controller equipments must be there. So the cost is increasing for tapping the power in between. The 4th limitation is your limited overload capability. So as I said, the point-to-point transmission is another problem, and another problem, that is the limited overload capability of the system. It is not due to the transmission line, it is due to the power electronics devices that we are going to use. You know, the power electronics devices, basically they are based on certain voltage and current rating. If you are exceeding, there will be excessive loss in that, and thereby there is a possibility of that device, switching device, may damage. So it has a limited, the converters and inverters are having the limited capability, and thereby we cannot go for the, even though for short duration, we cannot go for the higher rating or higher power or overloading of the system. So that is another problem here in this limited overload capability in the HVDC transmission system. Another concern here is the huge reactive power requirement at the terminal station. Terminal station, I mean that again, thus we are having here your rectifier end, that is the 3-phase here. We are having your inverter, and we require the reactive power support at these 2 terminal stations. As a thumb rule, if the rating of this line is 100 megawatt, we require the 60% of the reactive power sources at the both end of these converters. No doubt there is no reactive power involved in between. This is the converter. Now the question again arises, where is this reactive power goes? This converter system requires, because you know, if you see it is a normal thyristors, we will find the cos phi is your equal to your cos alpha. Alpha is your firing angle. If you remember the power electronics, the converter topology, if you are using the thyristors here, the power factor here will be equal to your this delay angle, cosine of the delay angle. Why it is required? Because we want to control the power, and this power control is basically controlled by the VDC, because here IDC is the constant. If you want to control the power in these lines, you have to change this DC, and the DC will be only changed from the highest value to lowest value by the firing of this alpha. You have to delay it. If you are delaying it, then what happens? If the more alpha, the power factor deteriorates. So here we require that compensating device to maintain that we should not draw huge reactive power from the AC system, because these sides are, we are having the AC system, here also we are having the AC system. So it is always better, because reactive power is a local phenomena, so we put here the reactive power sources, huge reactive power sources at the 2 ends. So normally as a thumb rule, we have to go for the 60% reactive power sources in both ends, and that is a very, very high reactive power sources are required. Even though sometimes we use here filters, they are also providing the reactive power support. We will see later on how they are, even though they are used for the filtering the harmonics. But at the fundamental frequency, if you will see, they provide the reactive power support, means they behave like capacitors. But other than that, still we require the reactive power support. If there is some problem here you are not having, then you cannot control the power here, because the controlling here the VDC we are talking. So we require huge reactive power support, at the two terminals. Now with the help of pulse width modulated schemes, with the GTOs and IGBTs, that value can be reduced. But still the IGBTs are not in the high voltage rating, so you cannot go for the high rating of this transmission system. But in the future it may be, and that reactive power requirement can be reduced, and thereby we can save huge amount of power and cost of the devices. Now another question may arise that the point-to-point transfer may not be advantageous. It may not be a problematic, it will be advantageous, because due to the theft here we don't want that people should tap the power. That as question arise here I don't want the people should go for tapping here. But here we are talking high voltage. The utilization is always at the low end and low voltage, and thereby here the DC system we are talking, it is for the high voltage DC, we are not talking about the low voltage DC. Then again as a same question arise when we will saw the evolution of the whole AC system. Because if you are talking about the low DC system, there will be huge I square R loss and your IR drop, the voltage drop will be there. So here the concern is we are talking about the HV, not LV. If you are LV, then these concerns will be there, you cannot operate the system. No doubt here the tapping is not there. Now the question arises to avoid the tap, no doubt some schemes are advised, and that is called HVDS. It is called high voltage distribution system. Means the transmission lines are high voltage, but again the customers are using the low voltage. So the lines which is running in the streets, it is high voltage, maybe 11 kV or 33 kV, and then they are putting a small transformer for individual customers. So that person cannot tap the power at 11 kV or 33 kV, and the small transformer is there, and from there it is given to the customers. So that third problem is basically minimized with help of the HVDS system, and normally it is used in the urban areas, especially in Delhi and Noida side. So we saw the advantages and disadvantages of HVAC and the DC systems, and now you can realize that the DC system is for the transmission is the better compared to the AC system. If you want, now again it's based on your objective. The first objective that you want to transfer the bulk amount of power. Second objective you want to control the power. Then these two options are very important and very good for this going for the DC system. Even though another advantage of the HVDC system that it can modulate the power over the AC system. I mean that you are having the two areas here and it's connected by a tie line, is the AC tie line. It is possible that we can have another DC system here parallel to this to stabilize this system. What happens this tie line, if it is weak, there is some problem here, this tie line may be tripped, and then system may be again problem. But this DC system, we can very fast control the power from one area to another area, and thereby we can stabilize both of the system very efficiently. So here the purpose is to stabilize the system. Then there is no consideration of the cost, there is no consideration of harmonics, and we have to go for this system because we want the smooth, reliable and secure and stable system operation. So now the three major objective I can say, one is we want, if you are going for the bulk power transfer over the long distance, the HVDC system is the best option. So I can write here this bulk power transmission over the long distance. Then HVDC is the better option. Second, if you are going for the power flow control. And third, that we have to stabilize the two area systems with help of HVDC. So the purpose is to provide the stability. So for these three purposes, I think HVDC is the better option compared to the AC system. That's why we are going for this HVDC along with the HVAC in the whole grid. In our Indian grid also, we are planning so many, already we have so many HVDC transmission lines are existing, but in the future its plan is much wider, much more HVDC links are there, because we want the power should flow from the northeast, which is far off, and that should come to Delhi side. And there is no other option because the distance is more than 1500 kilometers. So we have to just go for the DC lines. So many HVDC lines are planned, and in future we'll see the HVDC lines will be existing just parallel to the AC system as well. Now, looking all these advantage and disadvantage, let us see the various type of HVDC links. Those are possible, those are existing. So let us see the various type of HVDC links. Normally this HVDC links can be categorized in three broader categories. One is called monopolar, second is your bipolar, and third is your homopolar. This monopolar, as its name, the pole is one, means one conductor, and the ground is used as a return. You can see here in this is your, we are having only one conductor, and the ground is used here as a, the current is flowing through the ground. Normally this polarity here is used as a negative polarity rather than positive polarity. It is possible to have positive, it is possible to have negative, but the negative is preferred due to negative polarity will have the less corona loss compared to the positive polarity, and that is why this is operating at the negative polarity. The major problem here is that if there is any problem in this link, either in the converter or in the DC system, you have to stop the power flow, and completely it will be, the power cannot flow from either end. So this is a monopolar, means you are having only one pole, means only one wire, pole means wire, and the ground is used as a return. Another problem here, that during here the current which is flowing through the ground, there may be so many pipes, so many other devices inside the ground, that will be huge corrosion due to the DC current flowing there. So this is normally is not practiced in the system, but conceptually it is possible, because sometimes we will see the type 2 and type 3, they operate as a monopolar. So that is why it is explained that the monopolar you should know. Second category of the HVDC link is your bipolar. As its name, there are the two poles, means two poles here is that the two wires here. One is go, another the return conductor. In the bipolar here, you will see one conductor is on the positive polarity and another is on your negative polarity. To make this, you can see here in the normal operation, the current will not flow through the ground, because current will flow here through these converters, and this is your positive and another will be your negative, or vice versa. It can be positive, this can be negative, again based on the operation of the converter. So there are the two conductors, means two poles are there, one operates at positive polarity and another operates at the negative polarity. Here advantage of this system, if there is any problem in any side of pole, if there is a problem here either in the converters here, any of the converter here, or in the line, we can just open these converters and we can use half of the link here and the power can flow. So half of power we can maintain. So whatever right now we are having from Rihan to Dadri, it is operating at your plus minus 500 kilovolt, and this shows the plus minus means one is operating at plus, another is operating at negative. So this sign is normally used in HVDC links. This shows that you are having a bipolar operation. The plus responds 1 and here, and negative here this. So this is plus 500, this is minus 500, means voltage difference between these two, it is 1000 kilovolt. So the advantage of this, that even as I said here, even the one pole is down, we can provide half of the power that is flowing from one end to another end, and that is the very advantageous. Otherwise what happens if one, for example here, if there is some problem here, you are not providing the power from one end to another end, and this is used for the bulk power transfer, and this is blocked. So you have to, it's your chaos condition and you have to manage your system. So this is your bipolar, and it is a very popular here. Another is your homopolar. In homopolar, the difference between the bipolar here, again we are having the two poles, but the poles are of same nature means both are operating at the negative. Again, due to the less corona loss, because they are operating at high voltage, see the 500 kilovolts. So, huge corona loss will be there, and thereby what we try to do, we try to reduce the corona loss by going for the both negative poles. But major problem here that this is the current is flowing here, this current is flowing and the ground is used as a return path. Once you are using ground return, again that creates a lot of problem to the system. Maybe some voltage is induced, sometimes corrosion is there, sometimes even though the ground rods are broken, that again that creates problem. So, this is also not very common. The advantage of here is, again, if there is some problem in one of the poles here, you can still use half of the pole and you can provide half of the power that can flow from one end to another end. So, this is the major difference between the bipolar and homopolar. So, normally in homopolar it is simply written, it is minus minus or simple minus, it is sufficient for this. Because if homopolar, it will be in the negative both poles, it cannot be positive because more loss, and we can operate the converter successfully in the negative voltage operation as well. So, we can broadly classify it in the three categories. Conceptually it is possible, but this is more popular, and half of this is a possibility. Suppose one fail here, you are going in the monopolar operation. So, that is why I explained the monopolar, but to reduce the corona loss etc. here, we can go for the monopolar and we can use the ground as a return path. In both cases here, the double of power is flowing from this monopolar, because this is the voltage, the current is rating of the pole is same. So, we are going to have here the voltage here multiplied by 2. So, twice of the power is flowing here. But no doubt we have the two monopolars here, one monopolar here, another here. Here also we are having the two monopolars. So, the power is double of the single monopole. So, these three category of HVDC links are basically practically possible, but the bipolar is the better option and it is existing in India and it is planned several. In India, we are going to have recently plus minus 800 kV DC system, and so many locations are planned so that we can go for the higher and higher voltage. Again, the concept of here going for higher voltage means you can transmit more power, because the current which is flowing here in these lines are limited, again the conductor size. If you are going for more conductor size to reduce the losses, then it will be very bulky, then you have to go for bulky towers and so many other problems will occur. So, it is also option that we can go increase the voltage and maintain the current same. So, the losses will be less and we can operate the system satisfactorily. So, today's lectures, now I can summarize that we discussed about the HVAC problems with the HVAC system. Then we saw the HVDC advantages, and also we discussed some of the limitations of HVDC system, and we found that if your purpose is the bulk power transmission, or your purpose is to power flow control, or to provide the stability to the AC system, then HVDC system is the better option compared to the AC system. And also we saw the three types of links, that is the bipolar, monopolar and homopolars are existing, and that is feasible, but the bipolar is most common. So, with this we will see in the next lecture about this various components of HVDC systems, and that we will discuss in the next module, next lecture. Thank you.